तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. So in our series of lectures on basic electronics, we will move on to the next one. Before we do that, as usual, let us recapitulate what we learned in the previous lecture. You might recall in the previous lecture we discussed about power amplifiers using transistors basically. Under that we discussed several subtopics like different types of coupling that is employed, how amplifiers are named after the type of coupling, RC coupled amplifiers or transformer coupling, things like that. And then we also looked at how transistors can be, amplifiers can be classified on the basis of the frequency of operation, like low frequency amplifiers, high frequency amplifiers, RF amplifier, audio amplifier, things like that. And then when we wanted to look at the power amplifier characteristics, then we had a discussion on the AC and the DC load lines on the characteristics. And we also saw the different classes of operation, class A, class B, class C and class D operation of power amplifiers. And then finally we also took some examples of the push-pull amplifier where we have two different transistors helping us to amplify off signals, the positive half and the negative half signals of the power amplifier. Now let us move on to the next lecture, which is basically another configuration, which is a very important configuration for future applications you would see in the later lectures. That is the differential amplifier. People call it differential amplifier, some call it also difference amplifier. They mean the same. The amplifier amplifies the difference in signal between two inputs. Obviously if you talk of difference, you must have two different inputs. So the difference amplifier is a extremely popular amplifier, and that is the one of the reason why it has also been made use of in many of the modern integrated circuit design. It can be looked at in a very simple way. As you can see on the screen, the difference amplifier basic configuration has got two transistors, Q1 and Q2, and you see they look very identical. If you draw a line at the center, you find both sides are symmetrical. You have one transistor Q1 on this side and Q2 on the opposite side. You have two resistors RC1 and RC2 corresponding to the transistor Q1 and Q2, that is the collector resistors, and you have one common emitter resistor. The emitter resistor Re is common to both transistors. So both the emitters are connected together and you have one single resistor Re connected here, and this VEE is a negative voltage source supply. You have to connect to a minus terminal, this to be connected to a plus terminal, and you can also have your common terminal. So you can immediately see here we have a situation where we require not one single power supply, as we have seen earlier in some of our lectures. We require a dual supply, because you require a plus voltage, minus voltage and a ground, reference ground. So this dual supply comes out because you require the amplification of both the signals, the positive half cycle and the negative half cycle. That is why you require a dual supply. So it is a very simple configuration if you look at it. The corresponding circuit symbol can be shown is shown on the right side. You can see that it has got two inputs Vi1, Vi2, which are basically the inputs into the base of the transistors Q1 and Q2, and you have two output terminals VO1 and VO2 shown on the right side, which are actually taken from the collectors of the two transistors Q1 and Q2. So the output one terminal from Q1 is taken as VO1 and the other terminal from the collector of Q2 is VO2. So this is two output terminals, two input terminals, and you have a dual supply. This is a very characteristic features of a difference amplifier or differential amplifier. There are different types of different amplifier combinations possible for us in the transistor amplifier. That is, you can have the input signal applied to either input, that means one of the input only, while the other input is connected to ground. When you use this type of an amplifier, it is called a single ended amplifier input, single ended input. For example, if two opposite polarity input signals are applied, the operation is referred to as double ended operation. You are applying voltages which are oppositely moving on the two input base terminals of the two transistors Q1 and Q2, then it becomes double ended. If the same input, sometimes what will happen, the same input will be applied to both the inputs, both Vi1 and Vi2 will be connected to the same signal source, then it becomes a common mode signal, because the signal now is common to both the transistors or both the inputs, therefore that is called common mode input. You can similarly have on the output side also. So if I, for example, in a single ended operation, a single input signal is applied, however, because the two emitters are connected together, this single input signal will modify the corresponding emitter currents and the collector currents, and this, because the two emitters are connected, this change in collector current, emitter current of one transistor can also affect the collector current, emitter current and the collector current of the other transistor, even though you don't apply any signal to the second transistor. I hope you understand what I am trying to say. Therefore, you would always be able to get output voltages from both the collectors, even though you are applying the input voltage to only one of the base of the transistors. You can still get the collector output from both the transistors. So this is single ended input and double ended output. In the case of double ended operation, the two input signals are applied to both the inputs, both the transistors, and the difference in input is what you get at the output at the collectors. So this is one of the very important configuration that we will be talking again and again. Then third one is the common mode operation. In this, the one single input from a signal source is applied to both the bases, both the input terminals, and therefore what will happen is you will get two different polarities at the two different collectors. I hope you can see that. I will try to explain this to you now, and therefore if I apply the same signal to both the inputs and if I take the output from both the collectors, you would expect there should be no signal, the signal should be 0, because one signal is in phase. So it will, if it is, this input is increasing, the output also will be increasing, the other output is out of phase, therefore when the input is increasing, that will be decreasing by the same amount, and therefore effectively the two will cancel each other, and what you get at the output should in principle be 0, right. This is corresponding to the common mode operation. But however, you know, in practical situations you would find the opposite signals do not completely cancel, and a small signal will result, because there will always be some differences in the transistor, in the gains, in the HFEs, in the resistors and things like that. Therefore, it is not possible for us to exactly match the two transistors and the two outputs, and therefore you will always get some residual voltage which will be coming at the output of the collectors. So, but in principle the common mode gain, that is the output voltage divided by the input voltage, will generally be very small, whereas the differential gain will be rather large by several magnitude. For example, 1 or 2 magnitude, it can even be for example 200 the difference gain, but the common mode can be just few number 1 or 2 or something like that, right. So, this ratio of the differential gain, the difference the gain for the differential input and the common mode gain is what is called very important parameter, a physical figure of merit, and that is called common mode rejection ratio. We will again refer to this at a later stage when we talk about operational amplifiers and all that. So, we have to remember 3 different things with reference to differential amplifier. One is the differential gain, the other is the common mode gain, and the third one which is related to these two is the common mode rejection ratio, which is just a ratio of the differential gain to the common mode gain. Now, before I go further, I will try to quickly explain to you how you get 2 different polarities. So, for example, if you now refer to the picture that you see on the screen, you can give an input signal. Let us say if I give an input signal due to which the base current is increasing. So, if the base current is increasing here, you know in a common emitter amplifier the collector current also will increase, the emitter current will increase, the collector current will increase. If the collector current increases, there will be a more drop from the VCC given by the ICRC component here, and therefore this voltage, when this base voltage increases, the collector voltage decreases. So, this relationship we have already seen in the basic amplifier, common emitter amplifier situation, and therefore you can realize that there is a 180 degrees phase difference between the input and the output when I give the input at the base and take the output from the collector of the same transistor. Now, what happens when I take the output from the second amplifier, but the signal is given to the same base, but I try to look at what happens to the voltage at the collector point of the second transistor. So, when I increase the voltage at the base, you can realize the voltage at the collector will increase, but what will happen to the voltage at the emitter? When this increases, you can realize the emitter voltage also will increase, because they are differing only by the VBE component here between the base and the emitter of the Q1, and therefore when the voltage at the base increases, the voltage at the emitter also increases. When the voltage at the emitter increases, this is connected to ground, the second base is connected to ground for the second transistor, but this voltage increases. Therefore, the difference which is responsible for the emitter current will, what will happen, will actually decrease here between 0 and this. So, this decrease will decrease the current and hence the collector current, and therefore less voltage will be dropped across RC from VCC, and therefore this voltage tend to increase. I hope you are able to see that. So, when the base voltage increases, the emitter voltage also tends to increase, and because this emitter voltage is also the emitter voltage of the other transistor, the difference in voltage for the base bias between the base and the emitter will decrease, and therefore there will be a decrease in the collector current in the second transistor that will correspond to an increase in the voltage at the output of the collector. So, when I give a signal source here, you find this signal will be in phase and this signal will be out of phase from the second collector. So, when I take that output from both the inputs, not with respect to ground, but with reference to VC1 and VC2 terminals, if I take an output, you can imagine if they are perfectly matched, I must get 0, they should cancel each other, one is increasing, the other is decreasing by the same extent, and therefore the resultant should be 0. So, that is what I was telling, when you give input to one of the base and take the output from differentially from the two collectors, you will get almost 0 voltage at the output. Okay. Having understood that, let us understand the DC bias condition first. We will first consider the DC conditions, and later on we will go into the AC condition by drawing the equivalent circuit and things like that in order to understand the working principles of the differential amplifier. So, now I will again request you to look at the picture on the screen where you have the difference amplifier, and you can see the current which is flowing through the emitter resistance Re can be easily calculated, because on this side it is ground and we know this is VBE between the base and the emitter, and you have minus VEE here. So, I can consider calculate what is the current that is flowing through IE. Okay. For that, first initially we connect the both the bases to ground, VB1 is 0, VB2 is also 0. Under this condition we will find out what is the DC currents and voltages at the collector, emitter and things like that. Now, with each base voltage at 0 volts, the common emitter DC bias I already mentioned to you, VE, what is the voltage at the emitter VE is 0 volts, that is at the base, minus VBE, and therefore it is minus 0.7 volts. That is the emitter is, if you go back to this, the emitter is above the ground, okay, by only VE, and actually it is this is ground, the current is flowing in this direction, therefore this should be negative, therefore it is more negative, emitter is more negative than the base, and it is by the VBE, and that is why we say it is minus 0.7, because it is lower than the 0 volts, minus 0.7. The emitter DC bias current, therefore we can calculate, is nothing but IE is the voltage across the RE, at the two ends of RE divided by RE. One end is at VE, the other end is at minus VEE. So, VE minus VEE by RE, which is equal to VEE minus VE, but VE we have seen is minus 0.7, therefore VEE minus 0.7 divided by RE is the current IE. And if you assume that the two transistors are well matched, then you can see it is the IE is obtained by the two emitter currents. There is one common current coming from this transistor, the other emitter current coming from this transistor Q2, and together they add and flow as IE through RE. So, if we know IE, I know this and this will have to be half of that, IE by 2 and IE by 2, because of symmetry. If these currents, emitter currents, individual emitter currents of the transistors are IE by 2, then the individual collector currents will also should be almost equal to IE by 2, because they are all IC is almost equal to IE, therefore IC is equal to IE by 2, the two collector resistors are all currents also IE by 2. So, if we know the collector currents and the two transistors, the resulting collector voltage at the two transistors can be easily evaluated. The VC1, the voltage at the collector of the Q1 is equal to the voltage at the collector of transistor 2 Q2 VC2, and that is VCC minus ICRC, that we have seen. We have to subtract the voltage drop due to RC from VCC, and that will be the voltage at the collector. So, VCC minus RC IC, in this case IC is IE by 2, therefore VCC minus IE by 2 into RC. So, it is possible for us, given a configuration, calculate the emitter current, the collector current and the voltage at the emitter as well as the collector. That is what we mean by DC bias condition. If you get all the voltages and currents, we are clear about the DC condition of the amplifier. So, let us take a simple example. I have given a small illustration here to calculate the DC voltages and currents in terms of the numerical values. So, I have assumed that we have a 9 volts battery for the positive and 9 volts for the negative, therefore, it is a dual supply with plus 9 and minus 9 with reference to ground, and the two collector resistors are 3.9 kilo ohms each, and the emitter resistance is also 3.3 kilo ohm as an example. So, now what is how do I understand the DC bias condition of this circuit? We can calculate IE as VEE minus 0.7 by RE, VEE minus the voltage drop VE across this divided by the resistor gives me the current. So, VE minus 0.7 by RE, VE is 9 volts, 9 volts divided minus 0.7 by RE is 3.3 kilo ohms. If I substitute these values, I find the current IE is approximately 2.5 milliamperes. So, I know IE. If I know IE, I know the individual emitter currents, they are half of that. So, IC is also half of that. So, IC is equal to IE by 2, which is 2.5 milliamperes by 2, and therefore, it is 1.25 milliampere. So, if you know IC, then you can also calculate the VC. The collector voltage VC is nothing but VCC minus ICRC, that is 9 volts minus 1.25 milliampere is the collector current multiplied by 3.9 kilo ohm, that corresponds to about 4.1 volt. So we know the VC, we know the IC, we know the IE, we know all about the DC conditions of the amplifier, right. So it is possible for us to understand the DC conditions. Now let us move on to the AC operation of the circuit. So when I want to look at the AC operation, you know, the power supply will have to be shorted, so that means the plus VCC and minus VEE, they will all be grounded, and so what you will get will be a modified equivalent circuit replacing the transistor with its equivalent model. We have taken the very simple model where you have the emitter resistance RE1 and you have got the current source beta times IB1. So this rest of the things we have assumed to be very small, and therefore the modified equivalent circuit is shown in the screen. You have the VI1, VI2, the IB1 and IB2 are flowing into the base. This RI1, RI2 are the internal resistance of the base emitter junction, and you have the current sources beta IB1 and beta IB2 in the two collectors, and you have the RC coming in parallel with that. So you have the common emitters connected and you have a RE here, therefore at the end of the RE the power supply is ground, so you have connected to ground. This is the AC equivalent circuit. We have seen similar discussions we had when we discussed about RC coupled amplifier and H parameters and other AC equivalent models and things like that. So I hope you can recollect that. Once we have this becomes a very simple circuit, then we will be able to obtain the various parameters and also try to look at what is the amplification gain of this difference amplifier, differential gain we can calculate. Okay, now to calculate the single ended AC voltage gain, we connect the second transistor to ground. The first transistor has got VI1, so the gain is, and we also see that we are not taking the output from both the collectors but from only one of the collector, VO1 alone we monitor. So single ended input and single ended output, that is what we are doing. So V output by Vi will be the gain for this difference amplifier. So let us see how it happens, how it comes. So we apply the voltage loss for the input, and then you can see IB1 is equal to IB2 is equal to IB, because they are very symmetrical, the base current should be same. RI1 should be equal to RI2, should be equal to RI, let us say, in the two cases. And since RE is very large, that the input circuit is modified now. You have the voltage source, you have the input resistance of the first transistor, this is RE connected to ground, and it is also connected to ground through the second resistor, base emitter resistor. So what you have is a simple source and two resistors in series. If you ignore, because RE is very large, we can ignore the contribution compared to the small r. Small r will be few ohms, we all know that, 25 millivolts by IE, that will be going to be very small, whereas RE can be in several tens of kilo ohms, and therefore this is very large compared to this, therefore we can ignore. When you do that, you can see that VI1 minus IBRI minus IBRI due to the second transistor should be equal to 0 by KVL, Kirchhoff's law, that loop equation. So that from these we can find out the IB should be VI1 by 2RI. From this equation we can, simple algebra we can find out. So you can also reasonably assume that the two transistors are close or almost matched, therefore beta 1, the current gain of Q1 is equal to beta 2, the current gain of the transistor, second transistor, and that I can call it as beta, the common amplifier current gain. So IC will be beta times IB, and that will be beta times, instead of IB I can write VI1 by 2RI from the earlier discussion. So what is the output voltage? The output voltage is ICRC, the voltage across the RC due to the AC current, and that will be beta times IBRC. Beta times IB is beta times VI1 by 2RI into RC. We all know what is that RI. The RI, small RI, is nothing but beta times RE, beta times RE, where RE is the emitter resistance, emitter base resistance. So beta times RC divided by 2 beta times RE times Vi, and the beta will cancel, leaving you with V output by Vi, the gain, to be RC by 2 RE. So this is an important relationship. So in a case of a difference amplifier with voltage applied to one end and output taken from one collector, the gain of the difference amplifier AV is equal to V output by Vi1, that is equal to RC by 2 RE, where RC is a collector resistance connected to the two transistors and small re is the base resistance, 2 times small re. This ratio is what we get as the current gain. So let us take a very simple numerical example. Again you have plus 9 volts, minus 9 volts, you have 47 kilo ohms at the two collectors and 43 kilo ohms for example at the emitter Re, and I impinge a small AC signal with a RMS value of 2 millivolts. So let us now first calculate the DC bias calculation, and then we will try to calculate what will be the AC gain. So for DC bias conditions, IE is equal to VE minus 0.7 by RE, that is 9 volts minus 0.7 by 43 kilo ohm in this case, and that is around 193 microamperes. So the IE is 193, therefore the two emitter currents will have to be half of them, IE by 2, that is 193 by 2, that is 96.5 microampere, and you can also see that will be the same as the collector current within approximations. So resulting in the collector voltage VCC is equal to VCC minus ICRC, that is 9 volts minus 96.5 into 47K, and what you get will be around 4.5 volts. So the collector voltage is at 4.5 volts when the emitter is around with a 0 bias. This is the DC bias condition. So what is the value of Re, small re? The Re is 26 millivolts divided by 0.0965, that should be a millivolt here, so that corresponds to 269 ohms. So we saw that Re is usually very small, that is 269 ohms. So what is the voltage gain? The voltage gain for AC can be calculated as V0 by Vi1, that is RC by 2 Re. RC is 47 kilo ohm, 2 into Re is 269, 2 into 269 ohms, that will be around 87. So this is the voltage gain of the difference amplifier. So if I tell you that the input voltage is 2 millivolts, then the output voltage can be easily calculated as 2 millivolts multiplied by the gain, that is 87 multiplied by 2 millivolt, it is around 174.8 millivolt. So around 175 millivolts. So that is what you get as the output voltage. So it is in principle possible for us to calculate what is the gain and the output voltage. Now let us look at the differential, that is the double ended voltage gain. If I apply signals to both the inputs, what will happen? The differential voltage gain magnitude will be beta times RC by 2 Ri again, it will not be very different, you can try as a small exercise, and therefore both the collectors will give this voltage. When I want the differential gain, you would find it is the difference in the two input voltages that I should take care, and so V differential is Vi1 minus Vi2. So I will calculate what is Vi1 by using RC by 2 Ri and Vi2, and then I will find the difference, that will be the differential voltage, and that should be multiplied by the gain factor to get the output voltage V output. Now I also mentioned to you there is a third configuration which is corresponding to common mode signals. So you can have both the signals applied common to the two inputs, single signal is applied to both the transistor inputs, then what will happen? What will be the gain of a common mode signal? That is what we are interested in now. So you can see in this picture the two bases are connected together by a single wire and the signal is connected to one of the base. So the same signal therefore in effect is connected to both the bases, and you take the output from one of the collectors, single ended output. Let us see what happens. Now what is IB? IB is whatever voltage you give Vi minus the voltage drop across the Ri and Re combination, right, because Re is very small, we are only taking the drop due to capital Re. So Vi minus 2 beta plus 1 Ib into Re. Why 2 beta plus 1 Ib? Beta plus 1 Ib is the emitter current IE, you know that, 2 times IE, because you are this current will only be corresponding to one of the emitter, and therefore you have to multiply by a factor 2 if you want to calculate what is the current across the Re. Therefore 2 times beta plus 1 into Ib multiplied by Re gives me the voltage drop across Re. So Vi minus this voltage divided by Ri gives me the base current, right. I hope you are able to see. So there is a voltage here, this input voltage minus this input voltage gives me the voltage between the base emitter, and that actually is a voltage generated by the internal resistance Ri of the transistor. So Ib is equal to Vi, we can multiply, there is also Ib here on this side, right side as well as left side. So if I group them together and rearrange, you would find Ib is equal to Vi divided by Ri plus 2 times beta plus 1 Re, as you see on the screen. And what about the output voltage magnitude? The output voltage magnitude V output is equal to IC RC, and that will be beta times IB RC, that is equal to beta times IB is given by this expression, I will substitute that and multiply by RC. So beta times VI RC divided by the denominator small Ri plus 2 times beta plus 1 Re. So this is what the output voltage is going to be for a common mode signal. So what will be the voltage gain? The voltage gain for the common mode I represent as AC is equal to V output by Vi, that will be beta times RC divided by Ri plus 2 times beta plus 1 Re. This is the expression that I get for the common mode signal. You can see that Re is very large. Previously we got RC by 2 Re, small Re. Now we are getting beta times RC divided by the whole expression. So because Re is very large, you will find this number could be very large than compared to 1, and therefore the overall gain, common mode gain, will be very small. Right, now we will try to do a very simple numerical example. Again we have taken the same circuit as before. You have the plus 9 volts and minus 9 volts, and your RC values are 47K and your Re value is 43K, and you get again the same 2 millivolts now, but connect to both the inputs, common mode signal. So the voltage gain magnitude we have already calculated, AC is given by beta RC divided by a small Ri plus 2 times beta plus 1 times Re, and if I substitute our beta, which is 75 given in the problem, 47 kilo ohm as the RC, Ri is 20 kilo ohm, and 2 times beta plus 1 is 76, 2 times 76 into 43K, and if you calculate this, it comes out to be 0.54. That means what? It is less than 1, that means nearly half. So what is going to happen? If I give an input which is common to both the transistors, then the output will be half of that. That is going to be attenuation, not amplification. That is why I said common mode gain will normally be small compared to differential gain. Right. Now in principle we would like to have a common mode gain which is very small compared to the differential gain, so that the ratio which I referred to earlier as the common mode rejection ratio should be a very large number. We would like the amplifier, because it is called a difference amplifier, the amplifier should amplify different signals better than common signals. That is shown by the factor CMRR. In principle, if I want to explain in a simpler way, if I apply for example 100 millivolt to both the inputs, I will get one output, because that 100 millivolts becomes a common mode signal. Okay, let me take this example. I apply 100 millivolt to one of the base and 0 millivolt to the other base. I understand we have calculated also. The gain of the difference amplifier, let us say, is around 100. We got about 87 in our example. Let us take 100 as a very simple number. So I give 100 millivolt, the gain of the amplifier is 100, therefore I will get 10,000 millivolt, that is 10 volts at the output. Now with this condition I will get 10 volts. If I apply 1 volt as a common volt for both the inputs, that is, to one input I am applying 1.1 volt. 1.1 volt is 1 volt plus 100 millivolt. To the other transistor I apply only 1 volt. What is the difference between the two inputs? What is the differential input that I have given? It is the same as the previous case, just 100 millivolt. This is 1.1, that is 1, the difference is 0.1. 0.1 volt is nothing but 100 millivolt. So I have not changed the input at all, the differential input at all. So what should be the output? Output should again be multiplied by 100 differential gain. So 100 into 100, it should again be 10 volts. If this happens in any difference amplifier, then the CMRR is a very large number for this, almost infinity. Ideally if you get the same number, it is infinity, CMRR is infinity. But usually what happens, it is not, it will not happen like that. The transistor will be also affected to some extent due to the common signal that you applied, that 1 volt, and therefore you will get a finite gain for the common signal, and therefore CMRR will not be very large, infinity or something, it will be a reasonably number, small number. It is not as high as infinity, but it is not very small also, it will be reasonably high. Because it is a very important characteristic of a difference amplifier, we are interested in making that CMRR as large as possible. If you want a very large CMRR, the best way to do that is to have very good current source at the emitter. You must have a current source at the emitter. But you know, it is difficult to have constant current source. We can introduce it. That is actually what we require, is we require a very large resistance and a very large voltage source. If you have a very large resistance and a very large voltage source connected together, it can become a reasonably a good current source. So a good differential amplifier, as you can see on the screen, has a very large differential gain and very small, reasonably small common mode gain, AC. So the common mode rejection ability of the circuit can become considerably improved if we use the common mode gain as small as possible, ideally 0. So that means AC, which is given as V output by V input, beta times RC by RI plus 2 times beta plus 1 RE, what we designed last time. We see that larger the RE, smaller will be AC. If I put larger RE, the emitter current itself will decrease. So if you make RE small, large, you must also make VEE large, which is equivalent to saying I can replace the VEE and RE by a constant current source. When I do that, a constant current source, just now I was mentioning to you, is nothing but something which is obtained by applying a large voltage across large current, large resistance, so that the current is almost decided by the internal resistance rather than by the resistance I connect outside. So you can see in the picture now I have shown, in order to increase the differential gain and reduce the common mode gain, we want to increase the AC value of the RE to a very large number. For that we use a constant current source circuit. You can see in the picture we have removed the earlier RE and the VEE by a small transistor current circuit. If you look carefully, you can see it is nothing but a very simple transistor with a emitter resistance, and you have a R1 and R2. So this is a voltage divider bias and an emitter voltage, and this end, with reference to this end, this is negative, therefore the current is still flowing in the right direction. So depending upon the R1 R2, there is no base current, base voltage applied in the DC condition on AC condition. So with reference to the voltage divider bias, there is going to be some voltage now here, and there is also a voltage corresponding to VE, and this voltage will be decided by R1, R2 and the emitter current, and therefore this will be a constant like the current mirror circuit that I mentioned to you earlier. So this is going to be a constant current. The collector current here is going to be constant because it is decided by the RE value and the R1, R2 value of the transistor. So if this is going to be constant, the emitter currents also will be constant and the collector current also will be constant, and therefore the difference amplifier will perform well, and this constant current effectively is equivalent to a very large resistance connected in series with a very large voltage source, and therefore the very large resistance means the common mode gain will still be reduced, and therefore automatically the CMRR will be increased. Right, we have shown here on the screen the equivalent circuit of, yes, the same thing which we have drawn earlier with for the AC condition. For the AC condition, the power supply should be grounded. Here also the VE is grounded, and you have that constant current source here along with the corresponding output resistance, internal source resistance. So it is equivalent to high impedance in parallel with a constant current source, and we will try to do a small numerical example of how a common mode gain gets reduced when I use a current source. So we assume the beta 1, beta 2 is about 75, they are equal and equal to 75, and Ri1, Ri2 is around 11K for the two transistors Q1 and Q2. So if you assume Re is equal to R0, the resistance of the internal resistance of the current source, which will be around 200 kilo ohm. So the common mode gains becomes beta Rc divided by Ri plus 2 times beta plus 1 Re, which we have seen already. This beta is 75, Rc is 10 kilo ohms in the example given, and small Ri is 11 kilo ohms, and 2 beta plus 1 is 2 times 76, and Re is 200 kilo ohm. If we calculate it, it is coming to about 24.7 into 10 to the power of minus 3. That means it is a very small value. The common mode gain when I use a constant current source is found to be very small. So anything, if I divide the differential gain by such a small number, you know, the 10 power minus 3 in the denominator will go to the numerator, which will become 1000 times. So thereby you would find having a fractional or smaller than 1 current gain for the common mode amplifier, common mode scheme will certainly multiply the ratio of the differential gain to the common mode or the CMRR. So the CMRR will become a very large number. Now having discussed about the difference amplifier, now we should look at applications of the difference amplifier. One of the very well known application of the difference amplifier is in integrated circuit design, especially in operational amplifier. Most of the linear ICs will have differential amplifier as the input stage. There is a very specific reason why it is done. Now what do you mean by integrated circuit before I go into that? So what is an integrated circuit? In an integrated circuit, on a silicon chip you try to integrate the different electrical functionalities like devices like transistors, diodes, resistors, capacitors all together, and then you can form on the same silicon wafer a whole circuit. A circuit is made up of resistors, capacitors, diodes, transistors. So any one of these can also be made with a silicon. Therefore John Kilby, for example, and Robert Noyce really thought independently why a whole circuit cannot be done on a silicon chip by isolating some area as resistance, some other area as a diode, transistor, capacitor, etc. So integrate all of them and perform only interconnect the D component with some fine metallic wire like gold wire or something, then what you have on the silicon is no more a single device like a transistor or a diode, but a whole circuit. So it not only makes the device very compact, very small, but it improves the performance enormously. How do I say that? See, every transistor circuit, semiconductor device is very sensitive to temperature, as one of the example I can tell you. So when the temperature changes, the performance of the circuit will also change. Now if I have in the integrated circuits, if I make all the transistors and resistors on the same silicon chip, you can imagine the circuit will be very small and the components will be only few micrometers apart from each other. So a two transistors, for example, can be separated only by a few microns. Micron means 1 micrometer. If that happens, if there is going to be a temperature change, then you would find the two transistors will have almost identical conditions when they are formed in the transistor on the silicon chip, and therefore they will almost have identical characteristics. So when there is a temperature change, both will be affected equally. Hence, if I have a differential amplifier as the input stage, whatever that is same or identical to the two transistors will be rejected by the factor which we already know, the CMRR, common mode rejection ratio. So when I have difference amplifier as the input stage, you find the common voltages like the noise signals, the pickup signals, etc. will be completely rejected, and if there is any change due to temperature, that also will not affect too much, because the two transistors at the input stage are almost identical, and therefore they will have similar characteristics, and if one increases the other decreases exactly, and therefore when they combine together you do not get anything at all, 0 volts will be the output because it is matched. So this feature is one of the reason why difference amplifiers are used in integrated circuit design. There again is another important reason, and that is in an integrated circuit design it is very difficult to make capacitors. How do you make resistors on a silicon chip? It is very simple. If I dope the silicon with a pentavalent or a trivalent impurity, you would find the resistance will decrease. It will become either p type or a n type semiconductor, and a n type or a p type semiconductor has got finite conductivity at room temperature, and therefore they are basically something like resistors. So by controlling the doping, I will be able to get any magnitude of resistance on a silicon chip. I can always make a transistor or a diode on the silicon chip by selectively making some area p type and then making n type over and above that, or 3 layers means np, nr, pnp as the case may be, you can generate on the silicon chip. Therefore you can get transistors easily within very small regions, you can get diode within very small regions, you can get resistance by just simply doping the semiconductor in some region, and you can also get capacitance. How do you get capacitance? Capacitance is obtained by using diode, you know. Diode is a p-n junction device, and there is a depletion region between at the junction, and the p type and the n type, because they are conducting, they will act like metal plates, and the depletion layer in between acts like a insulator or a dielectric, and so what you have here is a capacitance. We have seen that earlier. We also discussed about the different types of diodes like the varactor diode, where this property of the capacitance of the junction is exploited in different applications. So now you have possibilities on the silicon wafer to make every type of electrical component that you want. You can make resistors, you can make diodes, you can make transistors, you can make capacitors. But there is one other problem. See, when you prepare the device, the doping will be controlled by the pressure and the flow and things, temperature of the process, where you let in a phosphorus pentoxide or whatever for doping. So the flow rate and temperature will all be controlled, and because silicon is a very small region, 1 inch or 2 inch wafer for example, then you find on that you can make enormous number, thousands of transistors and capacitors or resistors. But if I take one single set, you would find the doping is the same whether I want to make a resistor or a capacitor or a diode. The doping will be only decided by the parameters like the temperature, pressure, etc., and that will be the same throughout the wafer. And therefore what is going to happen is that under the same condition, if I want smaller resistance, that means I want more conductivity, I should dope more, but I cannot dope for longer period because the diode will and the transistor will not perform well. They require a very specific level of doping, and therefore the only way I can do that is by increasing the area for the resistance. For the given flow rate, given pressure and things like that, I have to increase the area of the resistor, region of the resistor on the silicon chip. And therefore if I want smaller and smaller resistances, then I have to use larger and larger area on the silicon chip. Similarly, if I want a capacitance, again larger capacitance if you want, you have to have larger area for the capacitance, and therefore you find the problem on the silicon chip now has become a problem of real estate, something like real estate. The area available is very small and you want to put different types of devices on that like resistors, capacitors, diodes and transistors. So you have to allocate different regions for the different components, and the values of resistors, if they are small, you will have larger resistance, larger areas for that. Similarly for capacitors, whereas for transistors and diode you can do it with a very very small region, and therefore you would like to avoid making use of capacitances, if possible low value resistances, because they occupy larger space. In that space you can as well make more number of transistors and diodes, and therefore in all integrated circuit the whole philosophy of the circuit design has now shifted from any component can be used for transistors. You now say if possible design your circuit only with resistors, diodes and transistors with almost no capacitance and none inductance, not even one inductance can be allowed. So you want to avoid capacitance and you want to avoid inductances. So you can only have in all your circuits diodes, transistors and high value resistors. These are all what is only possible. So the philosophy itself is changed. But how do I make an amplifier without a capacitor? You can immediately see one good scheme of making an amplifier without capacitance is the differential amplifier. You saw that there was no capacitors used in the difference amplifier. So if I use the difference amplifier as the input stage and couple it to other later stages for higher gain, you would find I can do away with the need for large coupling capacitors to take care of very wide bandwidth for the amplifier. So in the case of op amps, operational amplifiers, the input stage is a difference amplifier. And because it is difference amplifier, why do we use coupling capacitors in a normal amplifier? You want to only couple the AC signal and block the DC voltage. Again you can see in the difference amplifier without any capacitor you are able to do that, because the amplifier responds only to the difference in the input signals. I can use a difference amplifier and later couple to another stage of amplifier without worrying about using a capacitor to isolate the DC, because this amplifier itself is responding only to the difference between the two inputs, and therefore the only difference that you are going to have is only with reference to the signal, and all the DC will be equal and therefore they will be eliminated. So an input amplifier, input stage of an integrated circuit amplifier will have to be a difference amplifier, because thereby we can avoid the necessity for large value coupling capacitors to be integrated in the circuit, in the silicon wafer. And that is the reason why difference amplifiers are very useful, and that is why we discussed in this lecture about difference amplifier. You know, in the present lecture what I discussed today is I took a example of a difference amplifier which requires 2 transistors and 1 emitter resistance and 2 collector resistances, and we discussed the DC bias condition, how to calculate the various currents and the voltages, and we also saw by drawing the equivalent circuit how to obtain the AC gain for the common mode signal and for the difference signal and things like that. Finally we also saw how the common mode rejection ratio of the difference amplifier can be improved by introducing a current source in the emitter circuit instead of a voltage source VEE and RE. Now in the next class onwards we will start looking at the integrated circuits, their advantages over the normal discrete circuits, and how an operational amplifier can be used for different applications. Thank you very much.